All right. So as you've probably played around with the projectile motion lab on colorado.edu and some of their awesome physics simulators, you've probably noticed that we do not always have to fire at zero altitude. Okay, we know that for our initial calculations, pretty much everything was at zero, going to a zero altitude where the projectile ended. But that's not going to be true for all cases, and this is not necessarily something strictly within PLTW. This is something that you're going to see a lot more in an actual physics class, where you can actually have the differences in height. Okay? Now, in approaching this, and we've got the formulas within the PLTW formula sheet, but there are two things that you need to be keeping track of. Okay? One is we're going to have to factor in time. Okay? The change that happens from the initial launch, time equals 0, to whenever it hits the ground, the final time. And with that, we're going to have to keep track of the other concept, and that is making sure we know when we're dealing with our horizontal movement and when we're going to be dealing with our vertical movement, okay? And the different forces that are going to be applied to that. Because when we've talked about shooting a cannon straight out horizontally, we know that that's not necessarily going to stay straight. Okay? Gravity is going to take effect and pull it down towards the ground. But regardless of how much time, how much of the initial velocity is sent out, the time is going to stay the same. Okay? So what we're going to do is we're actually going to figure out how to calculate that. So to do this, okay, we're going to have to use this equation, okay? D equals, so distance equals the initial distance plus the initial velocity times time plus 1/2 of the acceleration times time squared, okay? So in this case, okay, in the projectile motion stuff, that means that we're going to go ahead and factor in that the distance traveled, okay? And this is going to be a vector value because we need to know that we're going down 10 meters, and we know that the initial distance, our starting point, is going to be our origin, our 0, 0 location. And our initial velocity, okay, even though we have an initial speed of 15 meters per second, okay, that's not counting the vertical changes, okay? The initial vertical speed is going to be 0. That same thing that happens when you're that skydiver jumping out of the plane. Okay? What we don't know in this equation is we don't know time, but we do know acceleration. Okay? We're going to consider our acceleration the same as the acceleration due to gravity, which is negative, keep those signs under control, 9.82 meters per second squared. Okay? All right. So in terms of what we know, okay, we know that that initial distance is that negative 10 meters. The initial distance, our starting point, is going to be our origin of 0 meters. We know that the initial velocity is 0 meters per second because we know that that's going to be the vertical movement, not the horizontal. Time is an unknown factor, okay, and that our acceleration, basically our gravitational pull, is that negative 9.82 meters per second squared. So when we start pulling in the equation, okay, and we're going to write it out to go ahead and just show you something, okay, D equals di plus vi times time plus 1/2 times acceleration times time squared. So our di value, okay, is 0. So we know that 0 is basically meaning we can ignore that. Okay. Our initial velocity is also 0, so we can ignore that because 0 times anything is 0, which means that we're simplifying this down to d equals 1/2 acceleration times time squared. So plugging in our numbers, negative 10 meters is going to be equal to 1/2 times negative 9.82 meters per second squared times time, which we know that is going to be in seconds squared, so because time is squared. Okay, so we're going to go ahead, take a moment, clear out our values. Okay, so we know that negative 9.82 meters per second squared times second squared, those units will cancel out. Okay, we'll get to the meters in a moment because we multiply both sides by 2. So 2 times negative 10 meters equals 2 times 1/2 is going to be 1. So negative 9.82 meters times time squared. We'll go ahead and divide both sides by negative 9.82 meters divided by negative 9.82 meters. That gets canceled out, leaving us with time squared. So negative 20 meters, sorry, forgot those units got canceled out. So negative 20 divided by negative 9.82. We know that those will both become positives, which means that that's equal to time squared. What we will still have to do is we're going to go ahead and have to do the square root of both sides. And in terms of calculator, we know that time is going to be equal to the square root of 20 divided by 9.82. So with the numbers factored out, the square root of 20 divided by 9.82 gives us 1.427 seconds. So time equals 1.42 seconds. Okay. So knowing that our time is 1.42 seconds, okay, that's a constant due to gravity. So it doesn't matter if the initial velocity, that initial speed, is 10 meters per second or 100 meters per second. Okay, the time that it takes for gravity to go ahead and pull that down, since it's shot horizontally, okay, there's no loss to its horizontal speed. We know that it's only going to be 1.4 seconds until it hits the ground. Okay, which means that we're able to use the second formula. Okay, the v with the bar over it. You may remember from some of math values, or you can look this one up in the mechanics section of the PLTW formula sheet. But that's the average velocity. Since our horizontal velocity is not going to be changing, okay, we can say that that could be 15 meters per second, it could be 2 meters per second, but whatever that is, because there's no loss, okay, horizontally, we can say that our change in distance is going to be our change in time times our velocity. Okay? Knowing our initial speed, okay, so this is where we're looking at horizontally, okay, v equals the change in distance divided by the change in time, okay, or we're going to have it basically rewritten as average velocity times the change in time is going to be equal to our change in distance. Okay, and this is all horizontally. Okay, so knowing that our velocity, okay, is going to be, let's say, 15 meters per second, okay, and knowing that our time is at 1.42 seconds, okay, we're able to go ahead and say, if the initial speed, okay, 15 meters per second times that 1.42 seconds, we know seconds will cancel out, and when we break out the calculator, we'll use the whole value rather than our rounded off one. So times the 15 meters per second. And that means that our distance, when we actually fire that cannon, should be 21.40 meters. Okay? So when we clear out our cannon, we leave it at that 10 meters of height, the initial speed of 15 meters per second. And knowing that we're expecting 1.42 seconds, we should be getting to 21.4 meters. Okay? So we'll fire the cannon. We see 3 stars, and when we break out the measurement tool, we can see that our calculations, okay, our seconds was slightly off, okay, although if we rounded it up, it would have been the same, 1.43 seconds. And our distance, pretty much the slight variation in terms of the actual distance. Again, rounding errors that are going to happen, but it should be enough to go ahead and see that that formula works, at least when we're dealing with horizontal lines. Okay, so again, a lot of things to kind of keep in mind. Knowing the differences between knowing the time based on the vertical change due to gravity, but knowing that the horizontal movement is not being affected, okay, are critical ideas. And this is why you are supposed to keep track of vectors, keep track of your the units of your values, because knowing that information helps you keep track of where the problem should be going. Okay, so that's how to do it with a straight line. We're going to go ahead and spend another problem going ahead and looking at what happens with angles. Okay, and this is where the math really steps up, and you're going to start realizing that your math classes really do have a big influence in terms of what you can do in engineering.